Hello. You should hear me now, and hope the desktop is visible. Does everything seem okay?
Yep,
Yes.
Okay,
everything's good.
great. And I got my speakers on. Okay. All right. So, okay. So remember, there's a homework assignment due today, and there's also a new homework assignment up there. Okay. So assignment 1 is due today, and there's a new assignment up there that's due in a couple weeks. And we'll start talking about this assignment today. But there's one last idea I want to go over about from assignment 1. Something that we'll be using it as the semester goes along, and assignment 1's a good example of this idea. So I just wanted to talk about one last thing from assignment 1. Then we'll start talking about assignment 2. Okay. So and also there's a reading assignment now from the operating systems textbook. Okay, so we still have some more topics in C to cover, especially for homework assignment 2. Homework assignment 2 makes you use some very tricky aspects of the C programming language. Now, that's one of the things we'll start talking about a little bit today. So we're going to start reading about operating systems, but there's more topics in C that we also have to talk about. So there'll be more reading assignments involving C. So we're going to do one chapter from the operating systems textbook to begin with, start operating system stuff, but then we're going to do a couple more chapters on C at the same time. Okay, so the reading assignment is to read this. This is a 6-page overview of operating systems. So read the first couple sections of it, the first 6 pages of it, up to this page here, page 6. If you want, you can read. We're not going to cover this stuff for quite a while yet. So yeah, you can read it if you want, but we won't get to it till much later in the semester. So the first 6 pages of this are what we're going to be talking about for the first half of the semester. Okay, virtual CPUs and virtual memory. Okay, so the topics are virtualizing the CPU and virtualizing memory. Okay, that's what we're gonna. That's most of the class actually. Those 2 topics. So that's a little overview of it. And then chapter 4 is the chapter on virtualizing the CPU, something called processes. So we're gonna homework, and your homework assignment 2 is Windows processes. So the idea of a process in the Windows operating system. So this is the main reading, this chapter here. This is what we're going to be talking about for a couple weeks. It's going to take us a couple weeks to talk about this chapter and the idea of a process. Okay, so that's the reading assignment. Okay, and
Professor, I just have a quick question about homework 1.
mhm.
Are we turning in our configuration file in our zip folder or just the
Oh, just a
filter.c?
filter. Yeah,
Okay.
when I test it, I'll build a configuration file and things like that to test it with. Yeah.
Okay, thank you.
So yeah, I'll create and delete. Yeah. See, if you notice that the test script that came with the assignment, it creates a config file and deletes it and then
Mhm.
recreates it. So you just submit filter.c.
Okay.
I'll compile it. I'll create a config file and I'll run it. Okay.
Okay, thank you.
So just the one file. You just need one file in the zip file.
Okay.
Right. Any other question about the homework, real quick, before we go on? Any other question about the homework assignment? Okay. All right. Okay. So start reading those 2 things about processes, and let me download the homework 1 zip file, and I'll download the homework 2 zip file also. And then there's a folder of there's a folder here that has more examples to help you get started with the homework 2. So just like homework assignment 1 had an example that was sort of like an introduction to homework example to the homework assignment. Yeah, remember there was this, besides homework assignment 1 zip file, there was this one that kind of gave you a good sense of what this one's about. Same thing here with homework assignment 2. Okay, so this zip file has a couple examples in it that are good examples for building up what's in homework assignment 2. Okay. Now, there's one idea I wanted to talk about today that's still from homework assignment 1. So let's open that up first. Okay. Now, you're writing a program called filter. And filter is actually kind of a standard term in computer science. You know, we talk a lot in computer science about filters. And this folder here says standard in, standard out, filters example. It's kind of a discussion of this idea of what do we mean by filters in general in computer science. Okay, so here's a C program called filter 1. Here's a C program called filter 2. Okay, so let me open those. I went opened it on my other monitor. There. Okay. Okay, here's the program filter 1. Okay, real simple program, just a few lines of code. Okay, it's got a main method, declares a variable int, a variable that's of type int. Then it says while. Then it uses the getChar program. getChar gets a character from standard input. Okay, so getChar gets a character from the standard input. It's a simplified version of scanf. For some examples, scanf could be overkill. So getChar is a little bit easier to use. It gets one character from the standard input. Now, I don't want to say it gets a character from keyboard, because that's what I want to start talking about and make sure you understand, get away from. Don't think getChar gets a character from the keyboard. I mean, that's the way almost everybody thinks about it. But you should think getChar gets a character from standard input. Okay, now it gets the character, it assigns it to the variable C. Then after that's been done, it checks that the result C is not end of file. So it loops while there's characters to get. So while there's something that's not end of file, keep looping. Okay, so this thing is reading characters from the input. Okay, if the character is greater than lowercase a and less than lowercase z, so that's a fancy way of saying if it's a lowercase letter, subtract 32 from it. Okay, what does subtracting 32 do from? Now notice that this is all kind of, C is a very strange programming language. C is declared as an int, not as a char. If I declare this as a char, this program's broken. Even though it says get char, you'd think that get char would return a char, but it doesn't work that way. C is just a really strange. We'll say a little bit about what's wrong with making this a char, but it's a int. So get char returns an int. Okay, that int holds a character. But in C, characters and ints are more or less the same thing. Every character is an int, though not the other way around. Okay, every character is an int. The characters are actually a subtype of int. So every character is an int, but some ints aren't necessarily characters. Which characters are ints, you find out by looking at the ASCII table. Okay, so you look up an ASCII table, and it tells you what all the characters are. These are all the characters that you could read from a keyboard. Okay. And they have a numeric value. See, they're numbered 0 through 127. Those are the numbers that happen to be. So those are the ints that are also char. An int between 0 and 127 is also a character. Okay. Now, here's a lowercase letter. It's 97. Lowercase a is 97. Uppercase a is over here, 65. Notice that if I subtract 32 from lowercase a, I get uppercase a. And that's true for all of these. See, if you take any lowercase letter, it has a numeric value. You subtract 32 from that numeric value, you get the uppercase letter. Okay, so this is 2 uppercase. Okay, this is in C how you write 2 uppercase. If you have a letter that's between, if you have a int that represents a letter between lowercase a and lowercase z, if you subtract 32 from that value, you've made it uppercase. Okay, all right. Now, if if C is between uppercase A and lowercase a, I add 32. Okay, so if the number's over here, I add 32 and put it over here. So what this program's doing is it's taking lowercase letters and making them uppercase, and taking uppercase letters and making them lowercase. So it's complementing the case. Okay, so this is the code. This code that will complement the case. Okay, now what if a letter is not one of these and not one of these? If it's not an uppercase letter and it's not a lowercase letter, the C program just doesn't do anything. See, if it's lowercase, it converts it to uppercase. If it's uppercase, it converts it to lowercase. Otherwise, it just prints it back out. So it echoes things that aren't lowercase and uppercase letters, so they don't get changed. Okay. All right. So that's, now let me compile that program and run it. And let's see, to compile it, I need my compiler. Oh, I didn't put a shortcut to my compiler there. Let me get a shortcut to my compiler. Okay. Okay. Oh, I do have a shortcut. Oh, I forgot. Yeah, I'm sorry. I have a shortcut to the compiler on my desktop already. I forgot I had it there. Okay, so there's the editor to let me compile the program. Okay, so compile it. Okay, and I'm going to run it in the command line. Okay, I'm running filter one. What's it doing? It's waiting for me. It's right now, the program is in this loop, waiting for an input, and it's going to do whatever I tell it to do. So if I type in 3, it gives me back 3. If I type in 44, it gives me back 44. If I type A, B, C, it gives me back capital A, capital B, capital C. If I type in X, Y, Z, it gives me back lowercase. And if I just type nonsense, see, the lowercase letters get converted uppercase, uppercase letters get converted lowercase. Things that aren't letters just get echoed back. Okay, all right, so that's the program doing what it's supposed to do. Okay, now how do I get out of this? Well, the program keeps looping until it sees end of file. What I type on a Windows machine to create end of file is Control Z. On a Linux machine, it would be Control D. See, now the program's over. Okay, now let's look at filter 2. It's a very similar kind of program. It has an integer variable that's being returned by getChar gets one character, it puts it in the int. It's not a char, it's an int, and it needs to be that way. We'll see why in a while. And then it checks if something is uppercase. Okay, if it's uppercase, it prints it. Okay? But then if it's any, but then it prints it again. Notice that what it does is if it's uppercase, it prints it. Then it prints any other letter it sees. What that does is it prints the uppercase letters 2 times, and it prints everything else 1 time. Okay, so let's compile and run this program. Okay. Okay. Okay, so here's filter 2. If I type A, just give me back A. If I type uppercase A, I get 2 of them back. Okay. Okay. Notice that when I typed capital H-E-L-L-O, capital T-H-E-R-E, I got back H-H-E-L-L-O, T-T-H-E-R-E. Okay, so it's just a funny little program. And if I type A, B, C, D, Control Z, hit enter, notice that Control Z didn't quite work the way it's supposed to. Control Z on Windows only works when it's the first character of a line. Okay, and on Linux, Control D, you can type it anywhere in a line. But on Windows, if you type X, Y, Z, W, Control Z, that on Windows, for some bizarre reason, Windows decide that's not end of file. Notice that the control Z is actually printed back as a weird little character. Okay. If I want end of file, I have to type control Z at the beginning of a line. On Linux, if you type control D anywhere in a line, that becomes end of file. Okay. Now, these two programs are what we call filters. A filter program in the world of operating systems is a program that reads from standard input and writes to standard output. Yeah. And what it is you can use filters. You can pass files through filters to do things to them. Here's what I mean by that. Now I'm going to start playing with this on the command line. If I take filter 1, I can send its output into filter 2. Now I've combined the two programs. If I type lowercase x, filter 1 sees lowercase x and does what to it?
Makes it capital.
And then filter 2 sees the capital and does what to it?
Prints it out twice.
Prints it out twice. If I give it capital X, what does filter 1 do to capital X?
Make it lowercase.
And filter 2 does what to the lowercase x?
Print it out once.
Prints out one time. Okay. So I've combined the two filters. Now, this is called a pipeline. And this is a pipeline of two filters. This is the metaphor for almost all big data these days. If you Google what is a data pipeline, you'll get gazillions of results. This is the metaphor for how we process data these days. Because now what I've got is the following. Okay. Control Z to end it. Here's another thing I can do. In this folder, I have a file called input. Okay. I want to process that data file. So I say filter 1, take your input from data.txt. So that data got, oh, let's see, what did I type wrong? Oh, input.txt, not data. Okay. My filter filtered that file. Now, if I want to do more data processing on that filter, I can run it through another filter. And then if I like that result a lot, I can save the results in results.txt. Okay, so what I just did is I took this input file and ran it through two processors, two filters, two data stages, and got back out this results file. Does anybody see why this is going to be useful? By just being able to type a line of code like that, what's the power of something like that?
We can process and organize data extremely quickly and efficiently.
Say again?
We can process and organize data quickly and efficiently.
Kind of, but what if I just sat here and typed the data? This is not very much data. I could have just taken this data and done the following even. I could have said filter 1, paste all that data in. What's the, let me see what, why do I want this program to read from standard input and write to standard output? How much data can you put in a file?
As much as you want.
As much as your hard drive will hold. Okay, you can put, and Google puts sometimes terabytes of data into a file. A command like this, that command there, that could be processing terabytes, gigabytes, massive amounts of data. In one command, I can process massive amounts of data and then save the results in a huge file. This is why people do think of this as big data pipelines. They have these, the pipeline is these filters. A pipeline stage is one of these filter programs, a program that reads from standard input and writes the standard output. And the idea is, the reason you want it to read from standard input is so you can hook the output of one filter to the input of another filter. So you can process the data through stages. Okay. And in the world of big data, what's common is that these filter stages usually do something to manipulate the data. Like one filter stage might look for missing data and it might look for bad data values and remove them. Another filter stage might look for data that needs to be somehow manipulated, pre-processed. Okay, and then another filter stage might do the actual calculation on the data, and then another filter stage might take that data and format it in a certain way. Like your homework, notice that your program, your homework assignment, the filter you're writing would be something that would take data and format it nicely. That could be one filter stage that takes random data that maybe, that for some reason the data is kind of messy and organizes it into neat columns. Okay, right? So that's how that's the modern world of big data. This phrase big data pipeline or just data pipeline, I mean, you don't even need the big data these days. People just think of them as data pipelines. Okay, yeah, it's a big part of it's. Have you ever heard of Spark and Hadoop? And these are the technologies that people use. You see, there's a little. There's this thing. The picture says Spark. That's one of the steps in the big data pipeline. Okay, that's one of the processes that can act like one of these filters. Okay, Hadoop is another one. Hadoop is another program that's used in these big. Another one is called MapReduce. So there's a bunch of phrases: Spark, Hadoop, MapReduce. These are some of the there's a whole bunch of them. Okay, so the metaphor these days for working with data is a pipeline, and it comes from the command line. Actually, their big data pipeline is not necessarily the same kind of pipeline. It's not happening at the command line. It's happening on a much larger scale. But they got the idea from these command line ideas. Programmers in the world of Linux and Unix and C and Windows have for years done things by having one program that reads in data, then the output of that program gets put into some other program that does something to the data. Well, I'm sorry. Then the output gets piped into something that does some more work on the data, then maybe another program that does some more work on the data, and finally you save the results in an output file. Okay, so you take data, read it into the first filter stage, the output goes into the second filter stage, does some more processing, that goes into a third filter stage, does some more processing, you save the output. Okay, and then you can take this line of code, and you can do what I've done over here. You put those lines of code, you take those lines of code and you make them commands in a batch file. So here's a simple batch file, filter 1 piped into filter 2. Okay, so if I run that batch file, I'm now running filter 1 piped into filter 2. Okay, so I'm running filter 1 through filter 2 until I get to the end, and I'm not saving the results, so when I quit, the program ends. So I can create little tools that themselves are batch scripts that run my filter programs. Okay, so that's another step in the direction of automating and making things more efficient. You have the programming language that we call the shell that you can use to write programs that run your programs. Programs that run programs. Okay, so these, like here's another shell script I put in here, a little bit more like this. This one just ran filter 1 through filter 2. This one's a little bit more elaborate. This batch file itself takes 2 command line arguments. Okay, so here's what I'm going to do. I'm going to delete results.txt. Okay, and Okay. I'm going to run this filter 1, filter 2 out in CMD. So I'm going to go over here and I'm going to run filter. Okay, there's that command line. Okay, now it takes command line arguments. Batch files can take command line arguments just like C programs can take command line arguments. In a batch file, the command line arguments are named number %1 and %2. %1 is whatever's the first command line argument, %2 is the second command line argument. What this do is going to say filter 1 will read from the first command line argument. The output of filter 1 will be piped into filter 2. Then filter 2 will save the results in the second command line argument. Oh, I'm sorry. Filter 1 will read from the second command line argument and put the results in the first command line argument. So I would go over here and I'd say results.txt. That's the file I want the answers to be in. Then I'm going to filter the file. It was called well, I'll filter the file readme.txt. This time I'll filter something else. I'll filter readme.txt. Notice that I don't use any IO redirection here. I say run filter 1, filter 2 out in with parameters results.txt and readme.txt. Then the first parameter ends up being see, there's where the redirection is. Filter 2 sends its output to that file, and filter 1 reads its input from that file. So now if I run this, okay, my output appeared in results.txt. There's the README file all mangled up. Okay, there's the README file all mangled up. Okay. What if I run this program without a second command line argument? Well, yeah, without a second command line argument. Okay. Notice I got an error. You know, there's no error handling in my batch file. So if you don't give it two command line arguments, the batch file kind of crashed. So type CLS clears the screen. Okay. Let me run that again. I'm going to run my batch file with only one command line argument, which is really kind of wrong. It expects two command line arguments, and I got an error message because when it tried to read this command, there wasn't a second command line argument. I don't know. Since there wasn't a second command line argument, I'm not sure what shows up there. But whatever showed up there caused the program to essentially crash. Okay. Now I could put error checking in. You can write these shell scripts much more elaborately. So I could do error checking and I could make sure there's a second command line argument before I try to use it. But here I'm just showing you that you can write scripts that make these pipelines that that themselves take arguments, a command line argument for there and a command line argument there. Okay. All right. So filters are a big part of computer science. And a filter is a program that it's the simplest kind of idea possible. Read from standard input, write to standard output. That way, when the program is running, the data might come from the keyboard, it might come from another file, it could come from another program. Notice that filter 1 can take its input from the keyboard. Filter 1 can take its input from a file. Okay. And filter 1 can take its input from another program. Okay. Filter 2 is going to process the README file, and its output's going to go into filter 1. So we saw filter 1 took its input from the keyboard. Filter 1 took its input from a file. Filter 1 takes its input from, oh, I misspelled README. Okay. Filter 1 took its input from another program. Filter 1 took its input from a file. and filter 1 took its input from the keyboard. Okay, see, that's real powerful. I didn't change anything in the filter 1 program. It read from the keyboard, read from a file, read from a other program. That's the real powerful thing. Filter 1 read its input from the output of another program. And then I could do the same thing with the input of filter 1. I'm sorry, the output of filter 1. Filter 1 can send its output to a file. Okay. Okay, filter, the output shows up now in, where is it? The output went to a file. Filter 1 can send its output to a file. Filter 1 can send its output to the keyboard. Okay. And filter 1 can send its output to another program. Okay. Now filter 1's output goes to filter 2 before it ends up showing up at the keyboard, at the screen. Okay. So filter 1's output goes to another program. Filter 1's output goes to the console. Filter 1's output goes to a file. And then, so you can have all these combinations. Filter 1 can be used. It could read from anything, and it can write to anything. The key is to write the program in this pattern, this style of a filter. Read from standard input and write to standard output. Printf is writing to standard output. Now, it's not writing to the console window. It's writing to standard output. GetChar is not reading from the keyboard. GetChar is reading from standard input. Okay, and then I can make this do anything I want with I/O redirection. Okay, what we call, well, we have two terms for this. When I do something like this with the greater than sign, that's called I/O redirection. I'm redirecting standard out to a file. This is called I/O redirection. I'm redirecting standard into a file. This is called a pipeline. It redirects one guy's standard out to another process's standard input. So a pipeline is also a kind of I/O redirection, but we usually don't call it I/O redirection. We usually just call this a pipeline. Okay. So I/O redirection are these two symbols, the less than symbol and the greater than symbol. Okay. Notice that you can, if you're careful, you can read this in a way that makes sense. Okay. Filter 1, the greater than symbol, you can think of as an arrow pointing at that. That means that the greater than symbol says filter 1's output goes to that file. Okay. On the other hand, this symbol, that file goes towards filter 1. Now, it doesn't matter what order you write these in. Like, you can write that, or you could write the other way around. Take your input from input and send the output to output. You do not have to write the input redirection and the output redirection in any order. So this says run filter with its input from input and its output to output. Now, those files don't exist. Oh, here's something that's important. If the input file doesn't exist, you get an error message. If the output file doesn't exist, it gets created. This is something that the operating system does for you to make this stuff a little bit easier. If you redirect on an input file, notice that there is no file called input. There's a file called input.txt. If you redirect on a file that doesn't exist, you get an error message. But if you redirect output to a file that doesn't exist, it gets created. Did you see it got created? And now the output will appear in it. The output's being dumped into that file. Okay, and the output was put into that file. All right. So that's real important to remember. When you do I/O redirection, if you direct input from a file that doesn't exist, that's an error. If you direct output to a file that already exists, it gets recreated. If it doesn't exist, it gets created. What if it already exists? Okay. If it already exists, it's the content is deleted and replaced with new stuff. Okay, now this file, it got emptied and filled back up with new stuff. Okay, it got emptied and replaced with new stuff. What if you don't want to empty the file? What if you want to add to it? There's a double arrow. That adds more stuff to input. Now, if I go over here, window, do I want to update this file? See, I updated the file. If I run the filter again, I'm updating, now this is called appending. Now I'm appending data. Zoom's getting in the way of the button that I need to click on. There, I had to, okay, see there. All right. So these are some of the, now what we're doing is we're looking at a language. We're looking at the shell language, the language that lets you write these CMD files. I could either write the language in a CMD file, or I can write the language at the console window. If I write the language in a CMD file, I'm writing a CMD program. If I type the language at the console window, I'm just executing as I go along. What I'm showing you here also works on Linux. The reason we use CMD and not PowerShell is because most of what we're doing here in CMD is valid in Linux. So all these little commands I'm typing here, they're valid Linux commands also. If you take filter 1 and filter 2 and compile them on a Linux program, in fact, I can do it in Linux here. I can go down here and open another command window, and I can switch to Linux on my machine. Okay, I just switched to Linux. I'm running Windows Subsystem for Linux now. So instead of typing dir, I'm supposed to type ls. Okay, so I'm actually running Linux at this point. But I can recompile like I'm going to take this filter program. Like, see, I'll do gcc -o filter 1 filter. Whoops. I'm going to compile filter 1 in Linux. Oh, I don't have Linux installed. Darn it. I haven't used this account. I haven't set up GCC. I haven't set up GCC into this account. Oh, let's see if I can remember let's see. Sudo. Just follow the rules, follow the instructions. I'm installing GCC. Hope it doesn't take too long. I've done this on my other accounts on this. You have to, one of the stupid things about Microsoft's Windows Subsystem for Linux is that when you install it, it's not installed on your computer. It's installed on one account on your computer. Then if you switch to a different account on your computer, like I have this account just for the classroom, so that I have a cleaner desktop and a more neat environment to work in. So I have a separate account for the classroom, but I forgot to install Windows Subsystem, finish installing Windows Subsystem for Linux on this account. Okay, let's see, almost there. Notice I'm running Ubuntu Linux inside Windows. 1 more %. Okay, well, this should finish. But I can compile this program over here, and pretty much the same things I type in this CMD window will be the similar commands that I type in this bash window. This is a bash window. This is a CMD window. And the commands I'm typing in here are pretty much the same. Okay, now, remember, couple rules that when you do IO redirection to a file that doesn't exist, the file gets created. When you do IO redirection to a file that already exists, the file gets overwritten. If you don't want to overwrite and you want to append, then you do this. And if you do IO redirection input from a file that doesn't exist, then the program, you get an error message. Okay, right? So those are things you have to remember, especially the IO redirection. Thing you have to be careful is it's real easy to clobber an important file by doing IO redirection to it. Because as soon as you do IO redirection to a file, the file gets emptied out. It doesn't get deleted. The file gets emptied out, and then new stuff gets put in it. But essentially, you can accidentally lose data this way. You can accidentally lose data by redirecting something to a file that you already have. Okay. Did this guy finish? Yay, this guy finished. All right, let me watch this. So GCC -O filter 1 filter 1.c. Okay. Notice I created, this is a Linux binary. This is a Windows binary. Okay. If I go to Windows and I try to run filter, oh, I'm sorry. That actually, when I type filter 1 here, I'm not running this file. Windows has a rule that if you can type the name of an executable without typing the exe at the end. So over here, when I type filter, I am running this program here. Now, if I make it not exist, now I'll go over here. See, now there is no filter program to run, and Windows will not run that guy. Windows won't run that guy. That's a Linux file. Okay, if you open it and look at the binary file, see how the first 3 letters in it are ELF? That's the name of a Linux file. ELF are the binary files for Linux. So this is an ELF Linux file. Windows won't run it. Okay. If I go over here, Linux, on the other hand, since it's a Windows machine, if I type filter, I have to do /filter. Oh, filter 1, I'm sorry. Okay. Notice it says it didn't. Okay. In Linux, if you want to run a program, you have to do /filter 1. So you have to put a little / in front. Okay. Now I'm running my program. Okay. Now I do Control D. See, as soon as I hit Control D, see how the program terminated? Let me run it again. So here's some input. Type Control D. There's the output, and the program's done. Oh, no. Oh. Oh, on Windows, it's not acting like Linux now. If I type Control D here, it's not acting as Control D. It's not acting as end of file. So I don't know if maybe it's Windows that forces that behavior. I have to type Control D at the beginning of a line, just like Control Z in Windows. A real Linux machine, I don't think acts that way. There are certain limitations. The Linux in Windows is sometimes in subtle ways a tiny bit different than a real Linux. Okay, but now I've got a Linux version of the program. But the thing is that things like I use the same symbols for IO redirection. So filter 1, take its input from input and write its output to junk.txt. See the command. So that read this file and sent the output to that file. Okay, so it read this one and sent the output to that one. Okay, just notice it's the same type, it's the same command. I would type the same command in Linux or in Linux. That's one reason I prefer to use CMD rather than PowerShell. These commands would look different in PowerShell. If over here we switch to PowerShell, using a filter in PowerShell, you don't use the pipe symbol. You don't use the pipe. Let's see, let me open a PowerShell. See, now I can go over here and I can, let's see, open power. So now I have a PowerShell prompt in that same window. Okay. Now this is in a lot of programmers work this way. I've now got 3 shells running in the same folder. Okay. I've got 3 shells running in that folder. Now, notice it's a little bit messy to be switching between these shells, and programmers know that it's messy to switch between shells. So there are programs you can run to organize your shells. And in the world of Windows, if you're going to run a lot of shells and you want to organize them, you run this thing called Windows Terminal, which you have to install separately. See, that's a window with 4 shells in it. And you can have a bash shell, a PowerShell, and a CMD shell. See, that lets you create, it's like a text editor for shells. You know, like you can have tabs here in files. Well, when you run terminal, you can create tabs that have shells in them. Each tab is a shell. And that way you can have one interface that holds all, like this interface holds all my files. That's nice. Okay. I have a bunch of files open. I can just switch between them. If I have a bunch of shells open, I would run terminal, and then I can have the shells all in one terminal. I haven't installed terminal's pretty new in Windows. It's been around in Linux forever, but Windows only recently added it last year, and I don't even have it on my machine yet. I haven't learned much about using it, but that would be a way to then organize this kind of stuff. I've got 3 shells, and instead of having 3 windows floating around, it'd be nice to have them all organized in one place. Okay, now if I go here to the PowerShell one, okay, I'm in this directory. Here's the program filter 1. Okay, notice that filter 1 didn't. Oh, I have to recompile that one. I'm sorry, I deleted the, or I can just go here and. Okay. I don't even remember. See, like here, I'm in this directory. See, I'm in the directory. There's filter1.exe. If I type filter1.exe, it doesn't even run. I can't even. Does anybody remember how to run a program in PowerShell? Anybody out there do PowerShell stuff?
Invoke expression is the command that you would use, or within PowerShell you can just type CMD to go back in the command.
Well, no, I don't know. I want to run. Yeah, my point is that PowerShell is weird. CMD and Bash look a lot alike, so that's a nice. I mean, CMD was meant to look like Bash. Bash came first. The Linux version came first, and when Windows wrote CMD, they made it look like Bash, except for a small number of things like Control-Z. PowerShell is completely different. So do you remember, you don't, like in PowerShell, how would I run? Do you know what I would do to run filter 1?
You can type invoke -expression --command, and then the command in curly braces.
Invoke expression.
-command. Yeah, actually a space after -command. -command is a switch.
Oh. Command.
They'll put filter 1 in curly braces.
It's some kind of argument.
Okay. Yeah, that should run. There's no input for filter 1.
Well, it's just read from standard input. Okay, no, okay, here's my point. PowerShell is bizarre. From my point of view, PowerShell is just flat out bizarre. Something simple like, I want to run a program. PowerShell all of a sudden says, well, you know, read 50 pages of our manual and then you can run a program. I don't know. I got real frustrated with PowerShell.
I've been using it for 10 years at work, so it takes a little bit of learning, but it's really focused on dealing with input and output as objects.
Yeah, but I know it's an object-oriented language, but how do I run
Yeah.
filter one? That didn't work.
I think it needs some input to it, because I
No,
think
it reads its input from standard input. See, filter one reads from standard input. Now it complained about the cannot evaluate parameter command. It didn't like that minus command.
hang on, maybe I got that command wrong. It's been a while since I've passed.
Oh, wait a minute, you're right. Its argument is specified as a script block and there is no input. So it probably doesn't, maybe it doesn't read from standard, maybe there's gotta be a way. Okay, let me try something here. Now, I know PowerShell is very powerful, but it's geared for writing scripts that do complicated things. And well, it's also meant to be used interactively. I'm not sure why it makes it so hard just to run a program.
It's better if you're like using PowerShell native commandlets.
Yeah, but this is not a commandlet. This is an EXE file.
That's kind of why they let you go back into the command shell if you need to in a hurry. But they do make it to agree with you, they do make it difficult to run plain old Windows shell commands within PowerShell.
So in PowerShell you can just type CMD and now I can run my filter program.
Yep.
See, so you can drop in and out of CMD. So now I'm done. Now I type exit and I'm back to PowerShell. See, now I'm in PowerShell, CMD. Now I'm in CMD, type exit. I exit from CMD and I'm back to PowerShell. So you can go in and out of CMD.
It's invoke command. So it's invoke dash command. I think that might be it.
That would make sense. So invoke. Now, do I need the curly braces still?
I don't think you do.
What's this? Okay, didn't like that either. Okay, okay. This is why I don't use PowerShell. PowerShell is a tool for certain kinds of things, but the main thing is CMD looks like bash. So if you learn how to use CMD, you're also learning how to use bash, which is really good. Okay, PowerShell is its own land. It's like the difference between learning Perl and learning C or something like that, or Python and C. Learning one doesn't help you do the other one. Here it's more like this is like Java and C#. Java and C# look a lot alike. Well, bash and CMD look a lot alike. I'm gonna quit PowerShell. Okay, but I want you to see that when you learn how to do this, the language of the command prompt, things like IO redirection, all those things work in Linux just like they do in Windows. Okay, the simple things that we do here, more complicated bash scripts aren't the same. When you do more complicated things in a command prompt versus a bash script, things start changing. But for simple things, specifically IO redirection and pipes and filters, they're the same. Okay, you work with them the same way. Okay, all right. So get used to the idea that when a program calls printf, it's not printing to the console window. When a program calls printf, think to yourself, it's printing to standard output. Kind of get yourself used to the idea that it's printing to standard output. Whatever somebody who runs the program decides standard output should be. It might be another program, it might be a file, it might be the console window. When you read, you're not reading from the keyboard. you're reading from standard input. Okay. And standard input gets to be whatever someone wants it to be. Okay. So if somebody wants standard input, when a person runs your program, they tell the shell program. Now, over here, when I run filter 1, okay, I type in to the CMD program this command that says set the input to filter 1 to be that file. Okay. So when I run this program, I tell CMD to do that IO redirection for me. CMD tells the operating system to do the IO. So I tell CMD to do the redirection. CMD tells the operating system to do the redirection. Then the operating system runs filter 1 with its standard input as that file there. On the other hand, if I do this, I'm telling CMD that I want the output of filter 1 to be redirected to output. CMD tells the operating system, run this program with standard output being that file. Okay, so now here I'm telling CMD, run filter 1 with the keyboard as standard input and the console window as standard output, and CMD tells the operating system to do that. How CMD tells the operating system what to do is the point of your next programming assignment, programming assignment 2. You're going to see how one program can run another program and tell the operating system how it wants it run. Things like, where should the input come from? Where should the output go to? So we're going to start talking about those kind of things. Okay, so we're going to see that we'll see baby examples. See, right now, CMD is running filter 1. CMD, I'm telling CMD what to do, and CMD is using my information to tell the operating system what it wants done. It's the operating system that actually runs filter 1, but under the direction of CMD. So one program is telling the operating system, please run this other program for me. The CMD program is telling the operating system to run the filter program. You're going to write a program that tells the operating system to write other programs, to run other programs. Okay. Now, there are pictures that go along with these ideas. If you see this README file, read this README file. It has really got some useful information in it. When you run a program, we call that a process. Here's a picture that everyone thinks of. Every process has 3 file connectors built into it. These are called file connectors. There's this one called standard in, one called standard out, and one called standard error. Okay. Every program comes with 3 file connectors. Okay. When you run the program, these guys have to be connected to something. Okay. If you don't tell the operating system otherwise, it connects this one to the keyboard and it connects these 2 to the console window if you don't tell it otherwise. So by default, standard in is connected to the keyboard and standard out and standard error connected to the console window. But under the you can redirect them and get pictures like this. Okay, I'm running a program. See, if I run foo using that IO redirection command and that IO redirection command, I'm setting up this picture. I now have standard in connected to the data file. See, I said standard in should come from data, and I have standard out connected to the result file. And I didn't say anything about standard error, so standard error is still going to the console window. Okay. Standard error is where a program is supposed to send its error messages. Most programmers just use printf to send error messages, but you're not supposed to use printf to send error messages because printf writes the standard output. There's a special place for error messages to go. You're supposed to use, I'll show you, you're supposed to use a different, you're not supposed to use printf for error messages because you should be using the thing that sends them to standard error. Okay. Here's what the picture would look like when you have a pipeline. I'm running a program called foo. There's foo. Now I'm running a program called bar. there's bar, there's a pipeline between them. So the standard out of foo goes through the pipe into the standard input of bar. Okay, that's the pipeline. Okay, but foo gets its input from data.text, and bar sends its output to result. And I didn't say anything about the errors, so both of these programs mix their error messages on the console window. So two programs are simultaneously sending error messages to the console window, and that can be a problem when you create these pipelines. The error messages can get garbled up. This is one of the slight disadvantages of running pipelines, is that you see here, the error messages are actually being combined together into the console window. Okay, so people who write these programs professionally do a lot of work to make sure their error messages are printed in a way that when you see them combined in a console window, you can say, oh, this error message came from foo, but this other error message came from bar. That's up to the programmers to make sure they write proper error messages. So this is a picture of what a pipeline would look like. We think of it as this guy's output just goes straight into this guy's input. Okay, this pipe we'll see later on is something called a buffer. What that means is that this program can be faster than this program. And so this program can be spitting out output faster than this program can read it. If this program is spitting out output faster than this program can read it, the data accumulates in this buffer. Okay, and that's the operating system does this for us. The pipeline is actually kind of a reservoir of data. So foo's dumping data into the pipe and bar's pulling it out of the pipe. And if foo is faster than bar, the data accumulates in the pipe. Then when foo's done, it can just stop, and then there might still be data in the pipe that bar can read out. And this is real common. This is one of the advantages of pipelines, is that these programs don't have to be synchronized. They can be, this one could be running fast and this one could be running slow. On the other hand, if this one's running slow and this one's running fast, this guy ends up looking at an empty pipe a lot. And what he'll do is he'll block. It's just like waiting for type, when a program waits for you to type something at the keyboard. So if this guy's slow and this guy's fast, this guy will just sit there waiting for input on that pipe very often. And then when the slow process dumps some data in the pipe, this one will grab it right away, process it, and then wait for some more data in the pipe. Okay, so the pipe's actually, the technical word is a buffer. The pipe is a buffer that holds data that's dumped by this process before it gets read by this one. Okay. Oh, and these two programs are running in parallel. This is a baby form of parallel programming. The foo program is running while the bar program is running. So every time foo dumps a little bit of data into the pipeline, bar can read it and process it. Foo might be preparing new data to dump in the pipeline, while bar is processing data it just pulled out of the pipeline. So this is going to be faster. Okay, here's this command here. I should have put this in the file and pointed out to you. That command there is somewhat equivalent to the following two commands. Okay, homework exercise. What do these two commands do?
Foo will run with the input from data.text, put its output in temp, and then bar will take its input from the temp file and put it into results.
Okay, so temp is acting like the pipe. See, temp is acting like the pipe. Foo's output gets dumped into temp, and then bar gets the input from temp. But this is not as good as this. Does anybody see why? Why is that better than this?
Because the other one you have to run it 2 times instead of just one long command.
Well, okay, yeah, because this does all of foo's processing first, and then does all of bar's processing. This potentially could take twice as long as this, because what this does is foo does a little bit of processing, puts data in the pipe. bar pulls it out of the pipe and does some of its processing. So bar is processing data simultaneously while foo is processing data. So this has the potential of being twice as fast because it's in parallel. Foo would run on one of your cores and bar would run on another core, and they would run simultaneously. Okay. Whereas this does all the processing of foo and all the now there's another disadvantage to this one. So this one is potentially twice as slow as this one. Now tell me another disadvantage. This one, the second disadvantage is a little bit subtle. Can anybody think of a second problem with the highlighted version? I'll give you a hint. Yeah, go ahead.
You're creating a text file that may already exist, and you might overwrite the data in there.
Oh, yeah, yeah, you're right. If temp happens to be a super important file you have on your hard drive, you clobbered it now. So you're right. That wasn't what I was thinking of, but that's a good point. You could, I used the word temp. Temp is actually a reserve. You should never call something temp because the Windows operating system purposely calls things temp. When it wants to create something temporarily, it uses the name temp. So you should not have data stored in a file called temp. But you're right. If you did, it could clobber. All right. So that's a bad thing. This could be clobbering some of your data. Okay. What else might be wrong with this? And I'll give you a hint. What if this file is 10 gigabytes?
That temp file is going to be 10 gigabytes.
The temp file is going to be 10 gigabytes. So what's wrong with this?
You're creating 3 10-gigabyte files.
Yeah, and you may not have room for them. You may have room on your hard drive for this guy and this guy, but you may not have room on your hard drive for this guy, and that guy, which is actually the case in Google land. In Google land, where these input files can be terabytes in size, there isn't space on the hard drive to create all of temp and then read all of temp out to results. There wouldn't be room on the hard drive for 3 data files. That's actually a common problem. This guy, why is that not a problem?
It's using the Windows system to pipe the data in rather than store it in a file.
Right. So all that data here, why is it not a problem here?
Does the pipe system not save it?
No, it doesn't. See, as soon as foo puts a little data in the pipe, right? Then what happens to that little bit of data in the pipe?
It's read.
Bar will grab it.
Bar will grab it and it's no longer in the pipe. So it does not, it only accumulates in the pipe until bar pulls it out. When bar pulls the data out of the pipe, it's not in the pipe anymore. So if bar keeps up with foo, the pipe will stay mostly empty. So you'll never get this huge amount of data like you would here. See here, all the data gets dumped into temp, then all the data gets read out of temp, and then probably what you would do here is do the following. See, usually then you would delete temp, but temp's going to stick around until you delete it. So this would create the temp. Remember, if the file doesn't exist, it gets created automatically, but you have to delete it. So these 3, actually, I should say these 3 commands are equivalent to this, because when you're done with this, there is no intermediate data laying around. When data gets put into the pipe, it immediately gets pulled out of the pipe by bar, and it does not linger in the pipe. Nothing that's been read. When data is read out of the pipe, it's gone from the pipe. It doesn't accumulate in there. And once it's read, it's gone from the pipe. So these 3 lines of code would be really the equivalent of this. Okay. All right. So, and then, this, you could draw a picture of this. This would be, if you thought of this as a picture, you'd have to have that picture with see, and then you'd have to have another picture This one would be foo. This one would be bar. See, it would be two pictures. Foo would run with text data going in and output going to temp. Then later on, bar would run with input from temp and out. So that these three commands are thought of as this diagram, okay? And this one command is this more complicated diagram, okay? All right. So these diagrams are real useful. If you start reading books about the Linux command line, you'll see these kinds of pictures appearing. People draw these kind of pictures to remind you of what, to give you a visualization of what a command line looks like. It's a way of visualizing a command line, okay? Right? And then, like here's some simple examples of filter. And you should think of what a picture would look like for each of these. What do pictures look like for each of those? Okay. And you can create multiple you can create, make this pipeline as long as you want. 10, 15 stage pipelines are real common in the data in the world of machine learning and big data. It's not all unusual to have pipelines that are many stages long. 10 stages aren't unusual. They do a lot of. Here's one reason why you do 10 stage pipelines. It's a lot easier to write 10 simple programs than it is to write one complicated program that does a lot of processing. So as a design feature, it's considered good programming style to design simple filters that do one little thing, and then you pipeline them together to do a complicated thing. This is sort of the Unix world. This is the Unix point of view of how to do data processing. Build simple filters that each one do something like you're taught to write functions. You're taught that when you write functions, they should do one thing. The single responsibility principle. It's actually in programming, it's got a fancy name. The single responsibility principle. Okay, that's the S in solid. Okay, write functions that do a single simple thing. Well, that's the same goal in filters. You write filters that do one simple thing. You write filters that do a simple thing, and then you chain the filters together to do complicated things. Okay, and the pipe is the key idea. The output of one filter goes into the input of another filter. Each filter should do one thing, single responsibility principle. The single responsibility principle is usually a principle for writing functions in Java or C or C++, but it actually it's also part of the Unix way of thinking of that's how they invented pipelines. A pipeline stage should have one responsibility. You don't want to write a program like foo that does a whole bunch of data processing. That's usually considered bad style. You shouldn't have foo do 27 things. You should have 15 pipeline stages that when you combine them together, they do the 27 things you want. Okay? And then those pipeline stages can be refitted into new pipelines, and they can be done, they can be combined in all kinds of different ways. Okay? All right. So you're writing, your homework assignment was to write actually what is actually a pretty useful filter. Like the filters I put in this folder are stupid filters. Change uppercase to lowercase, change lowercase to uppercase, duplicate, they're just dumb little filters. I wanted them to just be real simple code. You're writing a filter that's actually kind of useful. Take a bunch of numbers and format them into columns with the right number of decimal places. It's actually a useful filter. I think there actually is a filter like it in Unix. I think there is something in Unix that does something like that. Okay, so you're actually writing a kind of useful filter. And then filters like those can be combined with other filters to do data processing. Okay, now we run out of time. So what we're going to do on Wednesday is start talking about the connection between these remember over here I said that you're telling the CMD to run your programs. Okay, And what your next homework assignment is to start playing around with this idea of telling one program to run another program. Here I'm telling CMD to run filter 1. You're going to see how to write a program that tells the operating system to run another program. And we're going to call them processes. We'll see there's a subtle difference between the word program and the word process. Okay, so that's what we'll start talking about on Wednesday. So read the introduction to processes in the operating systems textbook. And if you have time, you can start looking at the code in this folder, homework 2 examples. If you want, that's what we'll be talking about on Wednesday, the code in this folder here. And that'll introduce us to what you have to do. That's a simple case of what you have to do in homework 2. Just like this was a simple case of what you had to do in homework 1. This is a real simple example of what you have to do in homework 2. So we'll look at that code and then we'll see how it affects homework 2. Anybody got any last second question? We've run out of time. Anybody got any last second question?
I was just wondering if I could go in your office hour like around 2:30, like I have it set.
Oh, sure. No, wait a minute. Office hours on Tuesday. I've got another class after this one.
Okay.
So I don't have office hour on Monday because I got a class right after this one. And I got class right up till dinner time. So if you got a real important question, you can send me an email. We can meet. But yeah, I can't meet. I don't have office hour today. But if you have something you want to ask, you can send me an email and we can meet. And then I have office hour tomorrow afternoon, like at 2:30. But I do have a class right after this one. I have class up until 5. So after 5, yeah. If you want to ask, if the homework's due this evening. So if you've got something important you want to ask before it's due, the homework's due this evening. I'm not super picky. I'm not really picky about homework assignments being on time. In the syllabus, it makes it sound like I am. Here's the reason why. If I don't sound real picky, at the end of the semester, I have students turn in all their homework assignments the day before final grades are due. Okay. I have to have a rule that basically tells students when they do something abusive, like turning in all the homework assignments the day before grades are due, I can just say, no, you broke the rules. If you turn a homework assignment in a few days late, I don't care. I'm not even going to grade them for a week it's going to be a week or so before I get around to grading them. So, you don't have to really worry about the due date, but don't turn in homework assignments 2 or 3 weeks late. Once I've graded them, then I may refuse to accept them after that. Okay. So if you look at the syllabus, it said basically, here's the most important part. If an assignment is more than 2 weeks late, then I reserve the right not to accept it. That's my real rule, okay? That's my real rule. That's to prevent people from being abusive and saying, oh, I turned in the homework, but they turned it in the day before grades were due. And people will do that. So that's the rule to kind of catch the people who are trying to abuse the system. So if you've got other things you're working on and you can't get it done tonight, or if you have questions and you still have questions to ask, please, ask questions. Get the homework done pretty soon. Really, what you really need to worry about is don't try to get it graded. Try to get it done before I get around to grading it. Okay? Yeah, and don't get it more. Don't fall behind in the class. Don't fall behind. Okay. Anybody got any other questions? Okay. So I'll go ahead and stop the sharing now, and we'll meet again on Wednesday and start talking about processes in the next homework assignment. Bye.